Our next speaker is Jayne Thompson from the University of Singapore. Sorry. The National University of Singapore, talking about causal asymmetry in a quantum world. Please take
right now.
I'll let you know. You've got 20 minutes or so and then some 5 minutes for questions.
Okay. Is it my turn now?
Yes, please.
Okay. I'm sorry, maybe your time zone is not what I thought it was. Okay. Okay, I'm sorry. I actually thought my talk was in 35 minutes time, but okay. Now? Yeah. Okay, so this is definitely a new experience for me, and apparently I'm learning on the fly about time zones as well as causal orders, temporal orders, and video conferencing. I am very sorry. I'll make amends by finding that Slack channel at the end of this presentation and answer any questions you might have. So what I will talk to you about today is a topic called causal asymmetry in a quantum world. And it's a collaboration between us at the National University of Singapore and the Center for Quantum Technologies, and also collaborators from Griffith University in Australia, as well as NIST, Imperial, Oxford, and University of California, Davis. So this is really quite an international collaboration. We had a wonderful time. Please do look my collaborators up. I'll leave links to them at the end of this talk. They're a truly fantastic bunch, and the work's really, really stellar what they do. So, okay. So the idea which underlies this presentation, the premise basically is that imagine we're watching a movie a little bit like this, and this is actually a clip of a guy who's knocking down a door in reverse time. And when I first saw this video, I was really perplexed. And intuitively, this sort of captures the idea that events are often a lot more difficult to rationalize, understand, and explain when they're presented to us in one particular causal order as opposed to in the opposite, say. So a hallmark example being watching a movie in reverse time can make it more difficult to comprehend and understand than watching it in forward time. So something like one of Christopher Nolan's films, such as the movie Memento, which is iconic for having its scenes scrambled out of chronological order, is actually a very intellectual challenge to actually understand. Because it's really only right at the end of the movie when we can piece together the disparate scenes that things begin to make sense. And by this stage, we're tracking a lot of information about the prior plot line to do this reconstruction. So this begs the question, are events generically more difficult to understand and comprehend when they're presented to us in one particular causal order as opposed to in the opposite, say? So in the sense that, do I need to retain a far more information about the sequence of preceding events in order to make a prediction about what's going to happen next? If I encounter the events in one particular causal order from left to right in a data string, say, as opposed to if I encounter them from right to left. And this actually turns out to be true. It's a well-known phenomenon in the topic of complexity science, known as causal asymmetry or causal irreversibility in the literature. And what it says is that if Alice wants to take the past and use it to make a statistically accurate prediction about the future, and her counterpart Bob here wants to take the future, use it to make a statistically accurate retrodiction about the past, then in general, Alice's task can be significantly simpler or easier than Bob's, in the sense that she may be able to actually execute it with a much smaller memory, or in the case of digital simulation, a smaller hard drive space. So we have a concrete example here, basically, to illustrate these ideas, and it's actually a box containing a fair coin, which is perturbed at each time step, causing the coin to flip with some probability p. At the end of the time step, the box announces the outcome of the coin flip by meaning a 0 if the coin lands in tails, and a 1 if the coin lands in heads. And in doing so, it generates strings of 1s and 0s, which look a little bit like this. But what I'm going to do is I'm going to post-process the string to turn the first 0 in each consecutive string of zeros into a 2. And the intuition goes that if I do this from left to right in a data string, then things are relatively procedurally simple. I simply scan along from left to right, and whenever 1 transitions into a 0, I say, okay, this is the first 0 in a consecutive string of zeros. I'm going to replace it by a 2. However, if I try to do the same task in reverse causal order from right to left in the data string, then now things appear like they might be slightly more complex. I'm now required to replace the last zero in each consecutive string of zeros by a 2. And to do this, I need to scan along and look at whether the preceding symbol is a 1 or a 0, and come back and modify my last output conditionally if the next symbol turns out to be a 1. So at the outset, this looks like it might be a task which is more easy to execute in one temporal order over the other. So we can actually formalize this intuition in the context of computational mechanics. This allows us to actually directly construct the memory optimal techniques to replicate these statistics in either causal order. And indeed, computational mechanics is a subdiscipline or sub-branch of complexity theory, which was originally invented to give us systematic tools for inferring the minimal amount of internal memory or structure a device must have in order to be capable of exhibiting certain observed statistical behavior. So in particular, given a complex system in our environment and a record of how the system has behaved so far in the past, computational mechanics gives us a systematic prescription for building a machine or a device, such that when we initialize this device in some memory state SX past, which is a function of what's happened so far in the past, there's a recurrent application of some physical process or map acting on this memory will cause it to generate a string of future outputs which are statistically indistinguishable from the future behavior of our real-life complex system itself. So if I were to encase my device in a black box, and analogously I place my real-life complex system in another metaphorical black box, then these two boxes would be operationally indistinguishable. There'd be no way to determine which contained the machine and which contained the real-life physical system. And computational mechanics gives us a especially clever trick for constructing the memory optimal such device, the one which is capable of making statistically accurate predictions about the process's future while retaining the least possible amount of information about the past. And this is true regardless of how we quantify memory or information in the memory. It's true for most popular quantifiers, such as the minimum dimensionality of the memory substrate system required to execute this task. It's true when we talk about the Shannon entropy of the distribution over internal memory states, or the information entropy of the memory, which is popularly considered to be the quantifier about how much information the machine is retaining about the past. In all these cases, this particular device is actually optimal. I'm sorry, I don't have time to go through the details of the construction, but there's actually quite a large body of literature out there describing it. So we can take these techniques and we can apply them to construct the memory optimal models in forward and reverse time of our simple coin process in this talk. What we find is that memory optimal model in forward time and reverse time are these two constructions here, the edge-emitting hidden markup models. And what this allows us to do is that we can directly prove that we only need to retain one bit of information about the past in order to make a statistically accurate prediction about the future, irrespective of the coin's probability of flipping p. However, in general, we need to retain far more than one bit of information about the future to make a statistically accurate prediction about the past, as shown here in this plot. Now, these two models are provably memory optimal. There's no other classical constructions which perform the same task while storing less information. So what this tells us is that this gap here, it tells us something fundamental about the process. It inherently takes less information to model these statistics in forward time than it does to model them in the reverse causal order. And this means that there's an inherent asymmetry in the process, such that when we seek the most mathematically distinct description of these events, there's a preferred causal order in which to reconstruct them in. So this particular gap or phenomena has become known as causal asymmetry or causal irreversibility, and people speculate that it's the origin of barbed arrow time, which is hard-coded into observational data. One more thing to note before I move off this slide is that these techniques are also provably memory optimal when we consider the minimum number of dimensions of the physical substrate required to execute these two tasks. So this means that a simple two-level classical memory substrate is sufficient to model these statistics in forward time. But if you want to try to replicate the same statistics in reverse time, we need a classical memory system with at least 3 distinct internal configurations, or a 3-level classical system. So these techniques are provably memory optimal. They're the best that you're going to be able to do. However, there's a really interesting catch, which is to say that we find that quantum mechanics can beat the provable classical optimum, which is to say that quantum mechanics can perform the exact same task while storing even less information in memory than this provable classical minimum. So in forward time, all we really have to do is take the two internal states of the optimal classical predictive model and associate them with these two quantum states here, and then afterwards repeatedly tiling at each subsequent future time step, a very simple quantum circuit based on these gates here allows us to make statistically accurate predictions about the process's future. Meanwhile, on the flip side of things, in reverse time, we simply need to take each of the three internal states of the optimal classical retrodictive model for retrodicting the past, and associate them with these three quantum states here, and afterwards, again, repeated application or current application of a very simple quantum circuit acting on the quantum memory of this device allows us to generate statistically accurate retrodictions about the process's past. Now, these techniques are, again, it turns out, provably memory optimal among all quantum constructions, which is to say there's no other way of executing these two tasks quantum mechanically while storing less information. So remember, this is a process of about an hour at a time. Generically, it took about 1 bit of information about the past to predict the future, but far more than 1 bit of information about the future to retrodict the past. However, what we found was that both the internal states of the optimal quantum predictive model and the internal states of the optimal quantum retrodictive model fit within a single qubit, which means this single two-level quantum system is sufficient to execute this task of replicating these statistics in either causal order. And this is already a departure from the classical case where a two-level memory substrate was sufficient to replicate the statistics in forward time, but in general we needed a three-level memory substrate to replicate the same task in reverse time. And indeed, this phenomenon persists when you look at the internal entropy of the quantum simulator. In terms of the von Neumann entropy of the optimal quantum predictive model is identical to the von Neumann entropy of the optimal quantum retrodictive model, which means that it takes the exact same amount of memory and information entropy to model this process in either causal order quantum mechanically. So the causal asymmetry completely vanishes in this process at the quantum level. There's no barbed arrow time at the quantum level in this process. And what we're actually seeing is that the barbed arrow is directly emerging when we restrict ourselves to using classical causal explanations for events. So what happens for arbitrary stochastic processes? Well, here we find that there's a systematic prescription for modeling the stochastic process in either causal order using quantum mechanics. In fact, the quantum models of these things are direct generalizations of the constructions on the previous couple of slides. And so in general, we can give you a systematic quantum algorithm or a systematic quantum circuit for generating predictions in either causal order, any stochastic process you give me. And generically, the quantum construction almost always stores less information than its optimal classical counterpart. And in a general stochastic process, we can think about causal asymmetry as a memory overhead penalty or a gap in the memory requirement, which you must pay when you insist on modeling the process in one particular adversarial temporal order. And this gap is an extremely generic phenomenon that happens for most stochastic processes. And what we can prove is that quantum mechanically you never need to pay this memory overhead penalty. In the sense that quantum mechanics can completely mitigate this gap, such that the quantum model running in the less causally efficient direction stores less information than its optimal classical counterpart running in the best possible causal direction. And in particular, this can be expressed as a theorem which says the quantum memory cost of modeling the process in some prefixed temporal order is always less than the classical optimum memory cost minimized over either temporal order. This theorem is completely general, so we can take it and we can apply it to arbitrary stochastic processes, including ones where the causal asymmetry grows without bounds. These are processes where it takes a small finite amount of information to model them in one particular causal order. But if we try to replicate the same statistics in reverse time, then the memory cost of modeling them diverges towards infinity as we amp up a parameter in the process. This is an example called the flower process, which exhibits this unbounded causal asymmetry. However, what we know is that quantum mechanically, we always can model it in either temporal order or storing less information than the minimum of the two classical directions. And this means that we directly garner scaling advantages, cases where the quantum models save an unbounded amount of information over their classical counterparts. And there's a lot of examples of this now. This is a generic phenomenon as well. So I've actually borrowed one from some colleagues, Miller Gu and Thomas Elliott. So it really nicely illustrates the way in which the classical memory cost of modeling the process diverges towards infinity as we amp up a parameter in the process, but the quantum memory costs remain small, finite, and bounded for all values of that parameter. These results also all apply if we consider the minimum dimensionality of the physical substrate we require to use as a memory to execute these tasks, which means that, for example, in the previous process, we just described the memory cost in terms of the physical dimensionality of the memory system you require to model that process in reverse time classically diverges towards infinity as we amp up a parameter in the process. But quantum mechanically, a single Q trip will suffice to model the exact same process. This means we also garner scaling advantages in the single shot regime by modeling things quantum mechanically. So we were able to experimentally demonstrate these results with collaborators in Griffith University in Australia who implemented the simple coin process in this talk for one time step into the past in reverse time. And what they were able to thereby show was the quantum dimensional advantage in memory cost. And that meant that they could take the optimal 3-level classical memory system for the optimal classical simulator and compress it inside a 2-level quantum memory and execute the exact same task. The experiment is extremely complex, actually. It's a 4-photon experiment. And in particular, I will be deferring most difficult questions about the experimental techniques to my absolutely outstanding experimental collaborators who are fantastic. You should really go talk to them. They are brilliant at what they do. However, from a theorist perspective, what we're doing here is the simulator has almost been entirely implemented by the bottom 2 photons, photon 3 and photon 4. And what's happening is that we're encoding past information directly into the polarization degree of freedom of photon number 3. So this 2-level quantum system or single qubit becomes our quantum memory register, implementing our quantum simulator. Afterwards, the subsequent series of entangling gates are entirely about entangling the memory register of photon 3 with an ancillary photon down here in photon number 4. And in particular, what this entanglement is doing is it's meaning that at the end of the time step of the simulation, when we collapse the path degree of freedom of photon number 3, you get the outcome of the experiment for that, of the stochastic process for that time step, and we simultaneously reconfigure or update the memory state of our photon 4 into the correct quantum memory state for continuing the simulation at the subsequent time step. So quantum simulator is able to use entanglement to automatically update and reconfigure its memory to take into account the last output of the stochastic process without needing to look at what that output actually was, which is something which its classical counterpart cannot do. And as a direct result of this, a quantum simulator happily builds superpositions of all possible futures of the stochastic process. Again, something its classical counterpart can't do. So the experiment was extremely successful. I'm going to breeze through these slides because apparently I'm running late. We had a 0.993 fidelity of reproducing the future statistics of the process, so very high agreement with the theory. What's more, we encoded everything into the polarization degree of freedom of a single photon, so we compressed a 3-level optimal classical memory into a 2-level quantum system, as promised, well, without sacrificing statistical accuracy. What's more, we could do tomography on the next state of the machine prepared at the end of the simulation, and we're therefore able to entirely reconstruct the internal memory state of the quantum simulator, and therefore infer its von Neumann entropy or the amount of information the simulator was storing. And so as a result, the top plot here on the left is actually directly demonstrating a quantum memory advantage in terms of information entropy that quantum simulator achieved over its optimal classical counterpart. So the experimental points are in red, and the black line illustrates the minimum memory cost of executing the same task classically. So our gap here represents how much of an improvement we got. The remaining plots are because the experimentals were able to generate more general stochastic processes and also witness the quantum memory advantage in these more general settings. So So I can get to my last slide and thank my collaborators. The takeaway message of this talk is that some things are generically, you have an intuition that they are more simple to describe and explain in one particular causal order over the other, say. However, this intuition can actually be formalized in the context of complexity science. It's known as causal asymmetry or causal irreversibility. But what we're finding in this talk is that the origin of this particular phenomena is a little bit more nuanced. It could be that one of the contributing factors is our proclivity to actually attribute a classical causal explanation to events, irrespective of the underlying mechanism which caused them to be generated. And I'm just going to leave you with my collaborators, because there's a lot of people who have contributed a lot of great work to this particular area. And in particular, a lot of experimental collaborators, who I'm sure you already know, and some great theorists as well. That's it.
Great. Thank you very much, Jayne, on behalf of the, I think it's about 250 people that were logged into your channel there. So thanks for a great talk. I've got one question here from Anonymous on the Slido channel saying, could you explain more detail on how a causal and a retrocausal state can fit into a qubit, please?
Yeah, a little bit. I've glossed some details, so I'm afraid you have to look at the paper and also some of the supporting literature. But what's happening is that the classical model, I'll just do the retrocausal. The classical causal model fits inside a single qubit, or in forward time, the classical predictive model fits inside a single qubit anyway. So of course the classical and quantum both fit inside a single qubit. Is in reverse time, the classical retrodictive model requires at least a 3-level system. And it's remarkable here that we can compress inside a single qubit because the classical retrodictive model is provably optimal. So we got an improvement of a classical optimum. So what's happening in reverse time is that every time there's a slight change in what it has to do in the future, in the past, every time there's a slight change in what has to happen in the past, based on the events which you have seen so far into the future, the classical model has to store each of these distinct cases separately. So if there's 3 different things it might have to do in this process in the past, which in this case there is, the 3 different possible statistical paths arising in this process, the classical memory has to store each of these in distinct configurations. Because it has to know to do something differently in these 3 different cases. However, as it turns out in this particular stochastic process, there's non-trivial overlap in the probability distributions of the paths. So while the paths are distinct in each of these 3 cases, they have some probabilistic overlap. Once you see the entire past, you still won't be sure which future it came from. And because there's probabilistic overlap in the different possible paths, even though there's 3 distinct categories of them, which you might see, the quantum simulator is able to actually compress the information by only storing the distinct states of its memory and to a level of distinguishability which aligns with the distinguishability of the different paths they correspond to. So classically, you get stuck storing them each in distinct memory states because you haven't got any other choice, but no other degrees of freedom classically. But quantum mechanically, your ability to sort of zip along the axis of the block sphere and access all of those other states means that you, because these paths are not entirely distinct, which you have to zip it in these 3 different cases, they're statistically in some case similar. You can actually store them in overlapping, not completely distinguishable quantum memory states. So it's got to do with a compression, which has got to do with throwing away even more information which was irrelevant to the past, but which classically you were being forced to store about the future because of the limitations of classical processing in classical memory space.
Great. I'm afraid we've got to move on to the next speaker now. So thanks again, Jayne.